We spend our entire life surrounded by motion, energy, light, and gravity, but most of us never see the simple rules quietly running underneath it all. Physics looks intimidating because it's written in equations, but here's the truth: equations aren't there to confuse us, they're just short sentences about how the universe behaves. In this video, I'm not throwing random formulas at you, I'm showing you the few equations that explain an absurd amount of reality, from why things fall to how energy moves, to why the universe even holds together in the first place. You don't need to be a physicist for this, you just need curiosity. Let's start with the equation that governs all motion in our everyday world. F is equal to ma. F is force, measured in newtons, essentially how hard you're pushing or pulling something. M is mass, the amount of matter in an object measured in kilograms. A is acceleration, how quickly velocity changes measured in meters per second square. This elegantly simple equation tells us exactly how objects move when forces act on them. The force you apply equals the mass of the object multiplied by its acceleration. Want to accelerate something twice as fast? You need to apply twice the force. Want to accelerate something twice as heavy at the same rate? You'll need twice the force. This equation is the backbone of all engineering, from designing cars to launching rockets. Think about pushing a shopping cart versus pushing a car. The shopping cart has low mass, so even a small force from your arms creates a lot of acceleration. It speeds up quickly. The car has high mass, so the same force from your arms barely moves it. Same force, different mass, completely different acceleration. Every time a car airbag deploys, it's using this equation. In a crash, your body has a certain mass and is decelerating rapidly. That's a huge force. The airbag increases the time of deceleration, which reduces the acceleration, which reduces the force on your body. Engineers also use this equation to design earthquake-resistant buildings, calculate rocket thrust needed to escape Earth's gravity, and even to design amusement park rides. Universal gravitation. This equation explains why apples fall and planets orbit. F equals g times m1 times m2 divided by r square. Where F is the gravitational force between two objects, g is the gravitational constant, about 6.67 times 10 to the negative 11. A tiny number that shows gravity is actually a very weak force. m1 and m2 are the masses of the two objects, and r is the distance between their centers. This equation reveals that every single object in the universe attracts every other object. The force depends on both masses. Bigger objects pull harder, and it gets weaker rapidly with distance because of that r squared term. Newton's insight was that the same force pulling an apple down also keeps Moon in orbit. Imagine two magnets. They are very close together. The pull is strong. Move them twice as far apart and the pull isn't just half as strong, it's 1/4 as strong because of the squared relationship. And if you use bigger, heavier magnets, the pull increases. This equation is how we calculate satellite orbits. A GPS satellite needs to orbit at exactly the right altitude where gravitational force provides exactly the right centripetal acceleration to maintain a circular orbit. Too low and it falls, too high and it drifts away. We have also used this equation to discover planets around other stars by measuring the tiny gravitational wobble they cause in their parent star. And ocean tides, they're caused by the moon's gravity pulling harder on the side of Earth facing it, which this equation predicts perfectly. Perhaps the most famous equation in physics, E is equal to mc square. E stands for energy, measured in joules, m is mass, measured in kilograms, and c is the speed of light, approximately 300 million meters per second. That c squared means we are squaring that enormous number. This equation reveals one of the universe's deepest secrets: mass and energy are actually the same thing in different forms. A tiny amount of mass contains an absolutely staggering amount of energy because we are multiplying by the speed of light squared. That's 90 quadrillion. This equation fundamentally changed physics, showing that matter can be converted to energy and energy to matter. It explains where the sun gets its power and made nuclear energy possible. Think of mass as a tightly wound spring and energy as that spring released. Just like a tiny compressed spring can unleash a lot of motion when released, a tiny amount of matter contains an explosive amount of energy waiting to be released. The c square is like the conversion rate. An exchange rate that's incredibly favorable when a tiny bit of one currency buys you an enormous amount of the other. Every second, the sun converts 4 million tons of mass into pure energy through nuclear fusion. That's why it can shine for billions of years. Nuclear power plants convert less than 1% of the uranium's mass into energy, yet that's enough to power entire cities. PET scans in hospitals work by detecting gamma rays produced when positrons and electrons annihilate each other, converting their mass directly into energy. Even in particle accelerators like the Large Hadron Collider, we use energy to create new particles, converting energy back into mass. The equation that describes energy of motion, kinetic energy equals 1 half mv squared. Ke is kinetic energy, the energy an object has because it's moving, measured in joules. M is the mass of the object in kilograms, v is velocity, how fast it's moving, in meters per second. Notice that V is squared, which makes this relationship very powerful. This equation tells us how much energy a moving object carries. The critical insight is that V is squared, which means doubling your speed quadruples your kinetic energy. Triple your speed and you have 9 times the energy. This is why car crashes at high speeds are so devastating, and why even small meteorites can create massive craters. The energy increases much faster than the speed. Imagine dropping a ball from your hand versus dropping it from a rooftop. The rooftop ball isn't just falling from higher up, it's moving much faster when it hits. Because energy depends on velocity squared, a ball moving twice as fast hits with 4 times the energy. That's why it makes such a bigger impact even though it's the same ball. This equation explains why speed limits exist. A car traveling at 60 miles per hour has 4 times the kinetic energy of one traveling at 30 miles per hour, even though it's only going twice as fast. This means 4 times as much energy to dissipate in a crash. Engineers design crumple zones in cars specifically to absorb this kinetic energy gradually. Bulletproof vests work by spreading out the kinetic energy of a bullet over a larger area and longer time. When meteorites enter Earth's atmosphere, their enormous velocity means they carry devastating kinetic energy. The meteor that killed the dinosaurs was traveling at about 20 kilometers per second. The fundamental equation of electricity, V equals IR. V is voltage, the electrical potential difference measured in volts. Think of it as electrical pressure. I is current, the flow of electrical charge measured in amperes or amps. This is how much charge is flowing. R is resistance, measured in ohms, which opposes the flow of current. This beautifully simple equation tells us the relationship between voltage, current, and resistance in any electrical circuit. Higher voltage pushes more current through, higher resistance restricts current flow. It's the foundation of all electrical engineering and helps us understand everything from why birds can sit on power lines to how to design computer chips. Think of water flowing through a pipe. Voltage is like water pressure. Higher pressure pushes more water through. Current is like the flow rate, how much water is moving. Resistance is like the narrowness of the pipe. A garden hose with high water pressure but a very narrow opening will still have low flow because of high resistance. Every electrical device in your home relies on this equation. Your phone charger converts 120 watts from the wall to 5 watts for your phone, and Ohm's law determines how much current flows. When you blow a circuit breaker, it's because too much current is flowing, usually because resistance dropped, like a short circuit. Electricians use this equation to size wiring. Too much current through a wire with too much resistance generates heat, which can start fires. Even LED light bulbs are designed using Ohm's law. They need resistors to limit current so they don't burn out. And every computer processor, billions of tiny circuits, all obeying Ohm's law. The equation that describes all waves, from sound to light, V equals F lambda. V is the velocity or speed of the wave. F is frequency, how many wave cycles pass a point per second, measured in hertz. Lambda is wavelength, the distance between two successive wave peaks, measured in meters. This equation connects three fundamental properties of any wave. It tells us that wave speed equals frequency times wavelength. For a given wave speed, if frequency goes up, wavelength must go down, and vice versa. This applies to all waves: sound waves, light waves, ocean waves, and even seismic waves from earthquakes. Understanding this relationship lets us manipulate waves for everything from music to communications to medical imaging. Imagine waves in the ocean approaching a beach. If waves are coming quickly, high frequency, then each wave doesn't have much space before the next one arrives, so wavelength is short. If waves come slowly, low frequency, there's a lot of space between them, so wavelength is long. But both move at the same speed towards shore. This equation explains why radio stations have different frequencies. FM radio, around 100 MHz, has wavelengths of about 3 meters, which is why FM antennas are that size. They resonate at that wavelength. AM radio has 1 MHz, has wavelengths of 300 meters, requiring much longer antennas. Your microwave oven uses electromagnetic waves at 2.45 GHz, with wavelengths of around 12 centimeters. That's why the metal mesh on the door has holes smaller than that, so the waves can't escape. This equation helps us understand why blue light has shorter wavelength than red light, even though both travel at the same speed. The equation for stored energy due to height. Potential energy equals mgh. PE is gravitational potential energy, the energy stored in an object because of its position, measured in joules. M is the mass of the object in kilograms. G is the acceleration due to gravity, 9.8 meters per second squared on Earth. H is the height above a reference point in meters. This equation tells us how much energy is stored in an object simply because it's elevated. The higher you lift something and the heavier it is, the more potential energy it stores. This energy can be converted to kinetic energy when the object falls. Think of winding up a toy car. The more you wind it, the more energy you store in the spring, and the further it will go when released. Lifting an object against gravity is similar. You're storing energy in it. A book on a high shelf has more stored energy than the same book on a low shelf. Hydroelectric dams use this equation directly. Water stored high in a reservoir has enormous potential energy. When released, it falls through turbines, converting that potential energy to kinetic energy and then to electrical energy. Pumped storage facilities actually pump water uphill when electricity is cheap, storing energy as gravitational potential energy, then release it to generate electricity when demand is high. Rock climbers understand this equation intuitively. The higher you climb, the more potential energy you have, which is why falls from greater heights are more severe. Even playground swings demonstrate this. At the highest point of the swing, you have maximum potential energy and minimum kinetic energy. At the lowest point, it's reversed. The equation that describes how gases behave, PV equals nRT. P is pressure, the force gas molecules exert on container walls, measured in pascals or atmospheres. V is volume, the space the gas occupies, in liters or cubic meters. N is the number of moles of gas, essentially how many molecules you have. R is the universal gas constant, about 8.314. T is temperature in Kelvin. This equation reveals how pressure, volume, and temperature are interconnected for gases. Increase temperature and either pressure goes up or volume expands. Compress a gas into a smaller volume and its pressure increases or its temperature rises. This relationship governs everything from how your lungs work to how engines operate to weather patterns. Imagine a room full of bouncing balls. These represent gas molecules. If you heat the room up, increase T, the balls bounce faster and hit the walls harder, increasing pressure. If you shrink the room, decrease V, while keeping temperature constant, the balls hit the walls more often, again increasing pressure. More balls in the room increase N, means more collisions and higher pressure. It's all connected. Every time you use an aerosol can, you're experiencing this equation. The gas inside is under high pressure. When you press the button, you're allowing the gas to expand into a larger volume, the atmosphere, which drastically reduces its pressure. That's what propels the spray out. Car engines rely on this law. During the compression stroke, volume decreases, which causes temperature and pressure to rise drastically, making the fuel-air mixture ready to ignite. Weather balloons expand as they rise because atmospheric pressure decreases with altitude. Lower external pressure allows the gas inside to expand. Even your refrigerator uses this equation. Compressing refrigerant gas heats up more and allowing it to expand cools it down. The equation that measures how quickly work is done or energy is transferred. Power equals work divided by time or energy divided by time. P is power measured in watts. W is work done or E is energy transferred, both measured in joules. T is time in seconds. Power tells us the rate at which energy is being used or transferred. This equation distinguishes between total energy and the rate of energy use. Two machines might do the same amount of work, but the one that does it faster has more power. This is why a sports car and a regular car can both climb a hill, same work, but the sports car does it faster because it has more power. Understanding power is critical for everything from choosing appliances to understanding electrical bills to designing power grids. Imagine two people moving a pile of bricks from one place to another. Both move the same number of bricks, same work, but one person finishes in 30 minutes while the other takes 3 hours. The faster person has more power. They're doing the same work at a higher rate. Or think about climbing stairs versus taking an elevator. Both get you at the same height, same work against gravity, but the elevator does it much faster, so it requires much more power. Our electricity bill measures energy in kilowatt hours, which is power times time. A 100-watt light bulb running for 10 hours uses 1 kilowatt hour of energy, but that same kilowatt hour could run a 10-watt LED bulb for 100 hours. Athletes care about power. A weightlifter who lifts 200 pounds in 2 seconds has more power than the one who lifts it in 5 seconds, even though they did the same work. Electric vehicles have high power electric motors that can accelerate quickly, transferring battery energy to kinetic energy at a high rate. So that's a small set of equations doing a lot more work than they look like they should. They show up in motion, in energy, in fields, in places you don't expect, and that's why people keep coming back to them. You don't need to carry them around in your head. It's enough to know that underneath all the mess, things aren't random. That's it for this one.